Okay, so now we want to talk about exponential growth and decay. Towards the end of the last video, we were talking a little bit about the growth factor and the decay factor. So what we were doing is we were finding B, and B is, again, like I said, it's the growth factor or the decay factor. So if I have something like f of x equaling a times b to the x, this is the initial value, and this is the growth or the decay factor. So how do I know if the exponential function is growing or decaying? Well, it says here that if a is greater than 0, so I'm looking right here, if a is greater than 0 and b is greater than 1, the function f is increasing and is an exponential growth function. Alright, and then if a is greater than 0 and b is less than 1, then f is decreasing and is an exponential decay function. Alright, so let's kind of sketch those graphs. So we have growth, alright, if a is greater than 0 and b is greater than 1. Alright, and so our graph is going to look something like that. And this would be right here, that would be a. Alright, then we have decay. When a is greater than 0 and b is less than 1. Alright, and in that case, our graph's going to look something like this. Alright. Now, if I were to make a negative in this case here, alright, so if I were to make a negative, so again we have the form f of x equaling a times b to the x. So if I were to make a negative, what I would be doing is reflecting this graph right here across the x-axis. Alright, so what would happen if my a then is less than 0 and my b is greater than 1? Alright, so reflect this across the x-axis, and what you would find is then I would have a decay. Alright, so there'd be exponential decay there. Alright, and then if I reflect, make a negative here, I would reflect it across the x-axis. Alright, and so I would have my a less than 0 and my b less than 1. Alright, and then I would draw the graph, and you'd have something like that. And here would be growth. Alright, so, oops. So I got 4 conditions here, two conditions for growth, here and here, and then 2 conditions for decay, here and here. So you want to be paying attention to that as you work through the homework problems 31 through 34. Alright, so now what we're going to do is talk about transforming the exponential function. Alright, and here's a little bit of review. So remember with our transformations that when we change the inside of the when the inside of the function changes, we are dealing with horizontal change or change to the x, and when we're manipulating the outside of the function, we're going to be dealing with vertical change or change to the y. Alright, and so very quickly I just want to go through this. Again, this should be review, but if we're given that f of x equals 3 to the x, alright, what type of transformations take us from f of x equaling 3 to the x to these following equations here? So f of x equals 3 raised to the x plus 1. Alright, so we're adding 1 to the x. So add to the x, go left. So this is going to be a horizontal shift. So add to the x, go left. So horizontal shift to the left, 1 unit. So we're going to go left 1 unit. Alright, and so f of x equaling 3x, 3 to the x minus 2. So this minus 2 is on the outside, so it's going to be changing the y. So we're going to go down 2 units. Alright, f of x equaling negative 3 to the x. Well, this is the negative out in front, so this is a reflection. So we're going to reflect across the x-axis. Alright. Now what we're dealing with here is a negative x, so 3 raised to the negative x, so we're changing the inside here. And so this is going to be a reflect across the y-axis. Alright, and then here we have 3 raised to the 2x, so again we're manipulating, we're multiplying the x by 2 on the inside, so this is going to be a horizontal. It's going to be a horizontal shrink. And remember, with the horizontal shrinks or the horizontal horizontal shrinks or the horizontal stretches, the scale factor is the opposite of what you see there. So instead of a scale factor of 2, the scale factor is going to equal 1/2. So we're going to have a horizontal shrink with a scale factor of 1/2 there. Alright, so hopefully that will refresh and help us with the following examples here, A, B, and C. So we want to describe how to transform the graph of f of x equaling 2 raised to the x into the graph of the given function. We want to sketch the graphs by hand and support your answer with a grapher. Alright, so for A here, and we're not gonna sketch these, you can kind of sketch them on your own. We're just gonna go through the different transformations. So g of x equaling 2 raised to the x minus 1. So what are we going to be doing here? So what we're doing is we're subtracting 1 from the x. So if we add to the x, go left. If we subtract, we go right. So what we're going to do is we're going to, so for A, we're going to translate the graph f of x equaling 2 raised to the x by 1 unit to the right. Alright. For B, we have h of x equaling 2 raised to the negative x, so the x is negative, so that's going to be a reflection across the y. So we're going to reflect the graph f of x equaling 2 to the x across the y axis. Alright, and then in C we have 3 times 2 to the x. Alright, so we're multiplying the entire function by 3. Alright, and so that's on the outside, so that's going to be a vertical stretch of scale factor 3. So we're going to vertically stretch the graph f of x equaling 2 to the x by scale factor of 3. Okay, so now what we're going to start talking about is the number e. Alright, and I'm sure many of you guys have seen this. Alright, so This is what we call the natural base E, and f of x equaling e to the x is one of the basic functions that we went over in section 1.3, and it's an exponential growth function. Alright, and what this is, the definition of the natural base e, what it basically is telling us is that e is approximately 2.71. So if you were to plug in x, as x gets bigger, or as x goes to infinity, the limit, or what this is going to approach, is going to be approximately 2.71. So that's all what this is saying right here. In a few more sections, we're kind of gonna get into what this theorem says here. So it says that any exponential function f of x equaling a times b to the x can be written as f of x equaling a times e raised to the k times x. And what we're going to be able to do is eventually, I think in 3.3, is take this and convert it into this. Alright, don't have to worry about that too much right now. What this is saying underneath here is that if a is greater than 0 and k is greater than 0, then we're going to have a growth function going on. And then if a is greater than 0 and k is less than 0, alright, then we're going to have decay. Alright, and then here are two pictures. So this is the graphs of f of x equaling e raised to the k times x for k greater than 0. So that's this function, or this graph here. I forgot to put it on your notes, so if you want to add that in, go ahead and do that. And then when k is less than 0, we have this graph right here. So if k is less than 0, notice how we have decay. If k is greater than 0, notice how we have growth. Okay, now in example 5, we're back to the transformations again and describing them. Alright, so we have f of x equaling e to the x, and we want to describe the transformations that take us from that to these three functions. So for a here, we have g of x equaling e raised to the 2 times x. So we're multiplying x by 2. So here's what we're going to do. This graph right here is obtained by, so this is going to be a horizontal. So what we're going to do is, so let's say the graph g of x equaling e raised to the 2x is obtained by vertically, not vertically, by horizontally shrinking f of x equaling e to the x by a scale factor of 1/2. Okay, in B here, alright, this is e raised to the negative x, so the x is being multiplied by -1, which means that we're going to have a reflection across the y-axis. So the graph h of x equaling e raised to the negative x is obtained by reflecting f of x equaling e to the x across the y-axis. Alright, and then I'm going to get rid of this. Alright, so then part C here, so we're going to say the graph k of x equaling 3 times e to the x is obtained by, alright, so 3 is on the outside, so it's going to be by vertically stretching f of x equaling e to the x by a scale factor of 3. Alright, so again, hopefully these transformations aren't too difficult. They should be a review of what we've done in the past. Okay, finally we're going to talk about now the logistic functions and their graphs. So exponential growth is unrestricted. Alright, and so what that means is that the graph of an exponential function was unrestricted. So it got bigger very, very quickly and continued to get bigger all the way into essentially infinity. Alright, so there was no restriction on what my range was. Alright, so it got bigger and bigger and bigger. Now, an exponential growth function increases at an ever-increasing rate, and it is not bounded above. That's what we just said. In many growth situations, however, there is a limit to the possible growth. A plant can only grow so tall. The number of goldfish in an aquarium is limited by the size. And in such situations, the growth often begins in an exponential manner, but the growth eventually slows and the graph levels out. The associated growth function is bounded both below and above by horizontal asymptotes. So exponential functions, alright, no restrictions on the growth. Logistic functions, however, we are going to have we are going to have restrictions on the growth. So it's going to be initially going to start behaving like it's exponential, but then it's going to kind of flatten out. Alright, so it's going to look kind of like this this kind of real flat, like S-shaped graph. Alright, so this is exponential. Alright, and then this is logistic. Alright, so those are the difference between the graphs. Alright, we already dealt with these. Okay, now we turn our attention to these logistic ones. Alright, and so we have the logistic growth function written here, alright, in this form. And a couple things to point out is that our C, alright, our C here is what we call our limit to growth. So that's going to be basically what our graph cannot pass, if you will. Alright, that's going to essentially be our horizontal asymptote. And so if we look at this this next example here in example 6, alright, so we have to graph the function. We want to find the y-intercept and the horizontal asymptotes. Alright, and so for A here, f of x equaling all this, alright, so this 8 right here, that is my C, or my limit to growth. Alright, and so what you're going to have here with these logistic growth functions are two horizontal asymptotes. So let's write down those first. So the horizontal asymptotes, you're always going to have one at y equaling 0, so you're always going to have one at the x-axis, and then you're going to have one at y equaling 8, or again the where our 8 is our limit to growth. Okay, now it wants us to also find the y-intercept, and in order to do this, alright, much the same as we've been doing, we set x equal to 0 and solve. So we have f of 0 is going to equal 8 over 1 plus 3 times 0.7 raised to the 0 power. Anything raised to the 0 power is 1. Right, so it's just going to be 8 over 1 plus 3, and that's going to equal 2. So our y-intercept is 0, 2. And if I want to sketch a quick graph of this, alright, 2, 4, 6, 8, so we're going to go by 2's. So this is the horizontal asymptote, y equaling 8. Alright, here's my y equals 0, my horizontal asymptote, and then my y-intercept is 0, 2. Come on. Alright, and so the logistic function, remember, it starts out looking exponential, but then flattens out. Alright, and so that's what that graph is going to look like. Alright, last one. Let's do B here. Alright, so again, let's write down our horizontal asymptotes. We're always going to have 2 with these logistic functions. So we're going to have y equaling 0 is always 1, and then y equaling whatever this top number is. That's our limit to growth. So y equaling 20. The y-intercept, what we're going to do is plug in 0 for x. Alright, so 20 over 1 plus 2 times e raised to the negative 3 times x. Alright, and so what this is going to become right here, this e raised to the negative 3 times x, when I plug in 0 for x, that's going to equal 1. So I really have 20 over 1 plus 2, or 20 over 3, which is approximately 6.67. So let's graph this. Okay, so y-intercept, horizontal asymptote, y equaling 0, and then at y equaling 20, so let's go up by 5s. 5, 10, 15, 20. This is y equals 20 here. Alright, and then the y-intercept is approximately 6.67. That, and then we got this going on. Now, I hope this helps and you are ready to do the homework problems when you come into class tomorrow.